Every time you switch on a fan or charge your phone, a steam power plant is working silently behind the scenes. These plants are the backbone of power generation, especially in countries like India, where most electricity still comes from thermal power. In this video, we'll understand the working of a steam power plant in detail based on the fundamental Rankine cycle. We'll see how components produce electricity continuously 24 hours a day, 7 days a week. So let's begin. At its core, a steam power plant converts chemical energy from fuel like coal, oil, or gas into electrical energy. The Rankine cycle involves 4 stages: heat addition in the boiler, steam expansion in the turbine, heat rejection in the condenser, and pumping water back to the boiler. This closed cycle reuses the same water, making the system efficient and continuous. The boiler is the first and most crucial component, converting water into high-pressure steam using intense heat energy. Fuel, commonly coal, oil, natural gas, biomass, or even nuclear heat, provides this energy. Water from the feed pump first enters an economizer, where it's preheated by hot flue gases, improving efficiency. It then moves to the boiler drum, where it transforms into wet steam. In modern plants, this wet steam passes through a superheater, significantly increasing its temperature and pressure. The output is superheated steam at typically 150 to 250 bar and 500 to 600 degrees Celsius. Superheated steam improves turbine efficiency and protects delicate turbine blades from erosion. The next stage is the steam turbine, often considered the heart of power generation. High-pressure steam enters the turbine and expands through its precisely engineered blades. This expansion converts the thermal energy of the steam into mechanical rotational energy. The turbine shaft is connected to a generator, and this rotation ultimately produces electricity. Turbines can be impulse type, where steam strikes the blades, or reaction type, where steam flows and expands between the blades. Most modern power plants use a combination of both, with large power stations operating at around 3,000 revolutions per minute. A single turbine generator set can produce several hundred megawatts of power, highlighting their immense capacity. Once the steam leaves the turbine, it has significantly lower pressure and temperature. Instead of releasing it to the atmosphere, we send it to a condenser. Here, the steam is cooled and condensed back into water using cooling water from a river, lake, or a dedicated cooling tower. This process is crucial for several reasons. It maintains a vacuum at the turbine exit, which significantly improves efficiency. It also allows us to reuse the water, saving cost and resources, and reduces the energy required by the feed pump. Condensers are typically surface condensers, where steam and cooling water do not mix, or jet condensers, where they do. A well-designed condenser improves the Rankine cycle's thermal efficiency by lowering the exhaust pressure, making the entire system more effective. Next comes the feed pump, whose job is simple yet vital: to increase the pressure of the condensate water. It then sends this high-pressure water back to the boiler, completing the closed Rankine cycle. Modern power plants predominantly use centrifugal feed pumps for their continuous and stable operation. The pressure is raised from near-vacuum conditions in the condenser to the high operating pressure of the boiler. Let's visualize the energy conversion within the Rankine cycle. In the boiler, heat is added, transforming water into superheated steam. The turbine then expands this steam, producing mechanical shaft work. In the condenser, steam releases its heat and turns back into water. Finally, the pump increases the water's pressure, sending it back to the boiler to restart the cycle. This entire process is elegantly represented on a TS, or temperature versus entropy, diagram. The basic Rankine cycle typically achieves an efficiency of around 30 to 40%. However, modern plants significantly improve this through techniques like reheating and regenerative feed heating. Beyond the main components, a power plant incorporates several auxiliary systems. An air preheater uses flue gas to preheat combustion air, boosting efficiency. The economizer preheats feed water before it enters the boiler. An ash handling system efficiently removes ash after fuel burning, while flue gas treatment systems reduce pollution. Cooling towers are essential for cooling the condenser water. These systems collectively ensure smooth operation, enhanced efficiency, and environmental safety. Steam power plants are utilized globally because they can generate vast amounts of power reliably. They run continuously with high reliability and are often cost-effective compared to some renewable sources. In India, over 50% of electricity is generated from coal-based steam power plants. In the US, this technology is also employed in nuclear and solar thermal power plants, showcasing its versatility. Let's quickly recap the working of a steam power plant. The boiler converts water to steam, the turbine converts steam energy to mechanical energy, and the condenser converts steam back to water. The feed pump increases pressure and recirculates the water, and the generator converts mechanical to electrical energy. This is how the Rankine cycle powers cities and industries worldwide, providing the energy we rely on every day. If this explanation helped you understand the working of a steam power plant clearly, don't forget to like, share, and subscribe to Simple Gyan for more mechanical engineering insights. Comment below your next topic request, and let's continue learning together.